So, hi everyone. Today we will be discussing about what is curiosity-driven exploration and reinforcement learning. Basically, you might be facing some environments which have sparse rewards. So, we will first of all try to understand what are sparse rewards and why it is problematic, and eventually how curiosity-driven exploration can help us in overcoming that issue. So, let's get started. So first of all, we'll try to understand what is a sparse reward. So in some of the environments that you are in, where you're trying to integrate reinforcement learning, you won't be getting reward very frequently. You won't be getting rewards after every action. So for example, assume Mario. I think Mario you all must have played. So in Mario, if you set up a reinforcement environment learning such that the reward is given only when the stage is cleared. So in that case, you can imagine that the Mario starting from very initial point will be taking some 40, 50, 60 steps and then eventually would be leading to the end. But as I said you that the rewards won't be given for the initial steps when you're not reaching to the final state, and would be given only when you have completed the stage. So training such an agent becomes a bit hard. Why? Assume that your agent is naive, it has no training at all. In that case, it has to take a sequence of random steps to reach to the end goal. Makes sense, because eventually in a usual reinforcement learning what happens is that it is the reward that helps as a guiding force for the agent to learn gradually okay, if I took this first step, this is actually taking me to a positive reward, hence it is a good action to take. Past reward systems, you're not getting any reward for every action. So even if you take a wrong step, if you don't get a reward, if you take a right step, you don't get a reward, eventually the model is not able to learn, and convergence becomes very slow, and at times it is just not possible also. So here comes curiosity driven learning. So in curiosity driven learning, we'll be introducing a new concept called as curiosity reward also. So basically in a curiosity driven learning exploration, we'll be having two reward systems. One is a primary reward that is called as an extrinsic reward. So the reward the agent gets when he reaches some checkpoint or when the action is when the episode is completed. So primary rewards aren't given at every stage, right? As I discussed, this is the sparse reward that we're talking about. So primary rewards in a curiosity driven environment are sparse in nature. You won't be getting it for every action. They're coming from the environment and hence called as the extrinsic reward. Now the second part, the most important part that we will be discussing is curiosity reward. That is the intrinsic reward. So the reward the agent will get on exploring new areas in the map. So we will be setting up some architecture so that once the agent is landing into a new area, a new map in the a new location, he's getting more reward as compared to revisiting something that he has already seen. So the magnitude of this reward would depends upon the newness of the next state that is coming up. So for example, if you are playing Mario, eventually you enter some dragon world. So even in that case, it is a completely new world coming, and hence the reward would be more as compared to normal walking into a already seen game, already seen stage. So this is coming from self motivation of the agent. So more, the agent itself is giving reward to himself, and that is what is called as an intrinsic reward. So how this curiosity reward is calculated? So the curiosity reward is pretty easy to calculate. What we would be doing is that we would be feeding up the current state S and the action taken A, and the output predicted would be the next state. So we'll be taking up some neural network, say NN, and even some shallow neural network, and we'll be feeding it with current state, action, and then we are expecting the predicted next state. Now we'll be feeding the same current state and action to the environment, and we'll be getting the actual next state. And the difference between the two states will be our curiosity reward. So the bigger the difference, the bigger the reward is. This particular network that we would be using for calculating this curiosity reward is called as forward prediction model. Now in this particular calculation that we are talking about, that is so predicted next state minus actual next state as your curiosity reward can lead to a couple of major issues. So we'll be discussing that. One is a noisy TV problem. So this is pretty genuine. Just think that eventually what we're trying to do, we are trying to maximize the curiosity reward, because rewards are always maximized, right, in any reinforcement learning environment. So eventually what we are motivating the forward prediction model is to produce larger magnitude of error, because as I told you, next state, predicted next state minus actual next state is our curiosity reward. And as any reinforcement learning environment will try to maximize that reward, we are trying to maximize that error. So eventually it can be the case that the forward prediction model may start producing random or noisy next states as predictions, because just you can think that if you're producing random noise, then the error would be the highest. But you don't want to have this issue coming into your prediction model, right? Because you don't want to predict random states. right? Why it is called as noisy TV? Because when you're predicting a random noisy next to it, it may look like a noisy TV. That is, and whenever you don't have a dish in your TV, you might have seen some random pixels on your screen. That is why it is called as noisy TV problem. Second is a trivial randomness. In the curiosity reward, we want to just check out. We want to consider only the major elements, the newness in the major elements and not all the elements. So, like for example, again considering Mario only. In Mario, you must have seen that there are clouds also, some birds also at in the sky, right? Now, eventually, that cloud or bird is not making any contribution to the environment, right? They're just for aesthetics, right? Now, if the model is not able to predict those correctly, eventually they are getting added up in the curiosity reward that we wish to avoid. We wish to consider only the major components of the screen, major components of the environment, the newness in the major components of the environment. So now for this, we are introducing a new segment that is called as a inverse dynamics model. So basically, inverse dynamics consists of two neural networks. One is the inverse dynamics prediction model. So this prediction model intakes state S, the current state, and the next state, and then tries to predict the action. Now, this is pretty interesting. So, in case of forward prediction model, what we are doing is that we took a state plus the action, and then we're trying to predict the next state. In case of inverse dynamics, we are taking the current state and the next state, and then trying to predict the action taken for the current state. So, this is pretty interesting. Second is an encoder model. So, basically, in some complex environments like Mario, you would be having RGB images coming in. So this becomes very complicated. So encoder model will basically intake these states, these RGB images, and then converted them into some sort of an embedding just for dimensional reduction purposes. So right now we have introduced three new models. One is a forward prediction model that will give us a curiosity reward. Now we have introduced inverse dynamics model as well as the encoder model. So basically, now we'll be coming up with our final module that we call as the intrinsic curiosity module, that is ICM. So it is consists of three parts. Encoder model generates embeddings for current state S and next state S bar, right? Feed these embeddings to both inverse dynamics model that predicts as the action given two states, and forward prediction model that intakes the current state and the action and predicts the next state. So eventually, both inverse dynamics model and forward prediction model are intaking embeddings of the state and not the actual state. Just remember that. Now, if you go into the particular architecture that we are following, so let's see that how ICM as a module can be integrated with any of the existing algorithms. So basically, ICM is not a standalone approach. It has to be integrated with some of the algorithms. Like for example, it can be DQ and reinforce A to C or DDPG that I have discussed already in my previous videos. So here you can see that here is the encoder model that intakes current state and the next state from the environment, right? Encodes these states and send it to the inverse dynamics model, which predicts the action, and then back propagation happens, which is training both inverse dynamics model and encoder model. Do remember that though encoder models outputs are getting used at both inverse dynamics model and forward prediction model, encoder model is getting trained just by the inverse dynamics model by the back propagation of that. We are not touching forward prediction model for training encoder. So the encoded current state and action are then fed to the forward prediction model, which gives us the next predicted current state, next predicted state, and eventually we are calculating the mean squared error between the predicted encoded next state and the encoded next state, right? And then that MSC, that mean squared error between these two, is taken as the intrinsic reward. So so this is the assume it to be some DQ and reinforcer algorithm. We are deciding over the action, and then depending upon the action, we are getting the extrinsic reward from the environment itself, right? We're feeding that action, we are getting a reward. Now this intrinsic reward is coming from this ICM model that I've just now explained you, where we have three models: encoder, inverse dynamics, and forward prediction. Forward prediction is giving us the intrinsic reward basically by calculating the mean square error between the predicted encoder next state and the encoded actual encoded next state. So basically, whatever next state we get from the environment, we'll be encoding that also using the encoder, and rest of the algorithm remains the same. A few points to note: ICM can be integrated with any existing deep learning model. It affects the final reward only, right? Everything else remains the same. We are not deciding the next action, we are not deciding the next state using ICM, but we are just updating the reward using the ICM module. The output of the inverse dynamics model aren't used anywhere to train the actual deep learning model, right? So ICM is basically, if you can say, is just used for training the encoder model, right? Nothing else. So even if it is predicting some action or what, we are just not using it.